Okay, so a different kind of relationship that we're going to look at here deals with the triangle proportionality theorem. All right, so essential question: when a line parallel to one side of a triangle intersects the other two sides, how does it divide those sides? Okay, and you might kind of already see that because we're talking about the triangle proportionality theorem. So how does it divide those two sides? Well, there's a good chance it's going to be proportionally, okay? So the idea here, to kind of set this up, we're not actually going to do this construction because, well, I just feel like we don't need to. All right, we'll kind of walk through it, okay? So in letter A here, they had wanted us to draw a picture of a triangle. Draw a triangle and label it ABC, okay? And then for part B, they asked to take any point on AB, on that segment AB, and label it E. So they chose E roughly in the middle of AB there, roughly in the middle, okay, it looks like. And then they wanted to construct a line parallel to BC that goes through point E. So we use that angle copy construction, which then results in the parallel line through a given point, right? So they just copied angle B there by putting that arc, did the same arc up there, and then they opened their compass and did that little swipe there to then mark that swipe, and gives you the point you can draw from E through there, and then that gives us F over there where it intersects. Okay. So part D says, from this construction, why are lines EF and then, line EF and segment BC parallel? So can someone raise their hand and tell me what makes, from this, the way we constructed this line EF, what makes EF now, line EF parallel to that segment BC? What is true there? Yeah, Hunter?
Do the corresponding angles?
Ah, yes, we have corresponding angles, right? We constructed this angle AEF to exactly copy ABC. So we have corresponding angles congruent. Okay? So corresponding angles and I'll call them what? Angle AEF and angle ABC are congruent. I'm just going to use the symbol for congruent. So line EF is parallel to BC. And again, I'm going to use the symbols there rather than the words. Okay, line EF is parallel to segment BC. All right? So that's how we know they're parallel. Okay. So now the next part here says we're going to use a ruler to measure AE, EB, AF, and FC. And again, rather than have you guys all worry about doing that here, I'm going to do it real quick for us. All right, just to save on time. So let's see here. So AE, I'm going to find its measure. Then I'm going to find EB. All right, so I'm going to turn my paper here so I can measure this real good. I'm going to use my straight edge. All right, so I'll let you guys kind of see here as well. So let's see, AE. So I'm going to put my ruler up there. I'm going to take a look. And when I measured, it's like E. So like the dot for E is like right between two of my little millimeter marks there. So I don't know, we call that what, like 0.85 centimeters, I guess. Because if that's 0.8 centimeters and that's 0.9 centimeters, that's about halfway between. So we'll say about 0.85 centimeters for AE. Okay. And let's take a look at EB. So EB is pretty much the same thing, right? I put my little starting point there at E, and to B it looks like, again, it's right about halfway between the 0.8 and 0.9. So again, I'll say 0.85 centimeters. Okay. Then I also want to measure AF and FC. Ugh. Okay, AF and FC. So let's see, I'm going to turn that. Hopefully these will measure nicely too. Okay. And maybe what do we want to say for the length there? What is that about? Looks like about So it's over 1. It's just before the 1.5. So I'd say 1.4, yeah? 1.4 centimeters. And then let's do FC real quick. And F to C is also, yep, right about 1.4 centimeters. You can see it right there. Yeah, 1.4. Okay. Whoa, zoomed in. Okay. And so then we're supposed to compare the ratios, AE over EB. All right, but what will AE over EB simplify to? Yeah, it's just going to be 1, right? It's 0.85 over 0.85, so that's equal to 1. It's AE over EB. And then let's see here, AF over FC is going to be, well, 1.4 over 1.4, so that simplifies to just what? 1. And oh my gosh, they're the same ratios. So that means they are proportional. So they're the same number there. Okay, so this parallel line, this line that kind of cut our triangle, that split the two sides of our triangle, it looks like it split it into the same ratio, right? AE over EB is the same as AF over FC. Interesting. Okay. In fact, because it cuts it in this way, so for example, because AE is the same as EB, so I can like kind of put that there, because AF is the same as FC, we actually have a name for this segment EF here. You guys remember what it's called? A segment that joins the midpoints of two sides of a triangle? Yeah, Drew. Mid-segment. That's right. This thing's a mid-segment, actually, it ends up being, because of the way they constructed it. Okay. Now we'll look here and see that it doesn't have to be a mid-segment for this to be true, but in this case, the way it, they've set it up is a mid-segment. So interesting. All right. All right. So flip this over here. So question 1 says, how can you show that triangle AEF is similar to triangle ABC? So how do we know that triangle AEF is similar to triangle ABC? Oh, no Shannon. What do you say there, Evan? How can we say that these two triangles here, triangle AEF is similar to triangle ABC? What kind of similarity could we use there? I know I have like a bunch of markings on my triangle right now, but what could we use? We already have one pair of congruent angles.
Yeah.
So careful, we're talking about similarity, so we want to know similarity. There is a side angle side similarity, so we do know that, for example, I mean, you would be true. I mean, this side here is going to be proportional to this side. We can figure that out to a degree, but then we don't know anything about EF or BC. So we couldn't say side angle side, not necessarily. What else could we say here, though? Can you come up with anything else? No? Not sure? All right, how about Melissa? What do you say? Can we... Okay, angle. So what other? So I have one pair of congruent angles. Where do you see another pair of congruent angles?
Angle AFE and angle ACB.
Aha. Yes. And why do you know that they're congruent?
Because they're corresponding.
Yeah, I was going to give away that. Why are they congruent? Corresponding, whatever. Yes, that's right. Very good. Exactly right. They are. So how can you show that triangle AEF is similar to triangle ABC? They are similar by angle. All right, and then I'm not going to worry about the explanation. Okay, we have kind of the picture marked on the other side there. But of course it would be something like because, we have two pairs of congruent corresponding angles. Okay, so there's the idea. All right. So what do we know about the ratios of AE over AB and the ratios AF over AC? Now these are different ratios, right? If we go back, AE over AB, so AE over AB, and then AF over AC. What do we know about those ratios? Okay. So again, consider that, AE over AB, and AF over AC. And then Drew, I'm going to pick somebody here and then we'll see. So Mary, what do you say? What are we going to know? What do we know since this triangle is similar to the big triangle? What's going to be the relationship between AE over AB, that ratio, and AF over AC?
Will be proportional.
Yeah, they're going to be proportional. They'll be equal. They'll be equal. Exactly right. Those two ratios will be proportional. The ratios will be equal because the triangles are similar. Okay, remember that's something we talked about yesterday, about the triangle proportionality and stuff like that, okay? So we know that they're going to be equal because the triangles are similar. That's something we learned yesterday, though, okay? All right, so using our answer from step E on the other side, make a conjecture about the line segments produced when a line parallel to one side of a triangle intersects the other two sides. So anyone want to take a stab at that? What's the conjecture? What's kind of like a guess? Because again, we saw a relationship show up. Okay, what's a conjecture that we could make here about these sides? So like, for example, AE over EB, AF over FC. What's maybe a conjecture we could say? What do you think? Is there something we can say will always be true, or was this relationship, the AE over EB, the AF over FC, is that only true for this particular situation? Or can we say something in general then about the ratios? Any ideas? All right. Well, we'll move on then. So, explain one, proving the triangle proportionality theorem. So, as it turns out, okay, even though we didn't make a conjecture here, when you have a line parallel to a side of a triangle that splits the other two sides, okay, the parallel line splits those two sides into proportionate segments. So, AE over EB is going to be equal to AF over FC. Notice that in this case, E and F, do they look like they're the midpoints of their two sides there? Does E look like the midpoint of AB? Or does F look like the midpoint of AC? Yeah, no, it does not. And in fact, it doesn't have to be, okay? It still will make a proportionate relationship here. Okay? So, let's try this. We're going to go through this proof here. I think we should be able to do this okay. Okay? So, given that line EF is parallel to BC, so there's EF, there's BC, we want to prove that AE over EB is equal to AF over FC. Okay, so the step one is we want to show that this triangle AEF is similar to triangle ABC. Okay, so if you look through the logic here, because EF is parallel to BC, you can conclude that angle 1 is congruent to angle 2, and angle 3 is congruent to angle 4 by the what theorem? How do you know that 1 and 2 are congruent? How do you know that 3 and 4 are congruent? I think Melissa had said it. What are they, Melissa? Corresponding angles theorem, that's right. Okay. So as a result then, Melissa, triangle AEF is similar to triangle ABC by the... So, well, careful. We're concluding that two triangles are similar. So what do we... There you go, exactly right. By the angle similarity. That's one of our shortcuts, right? Okay. So we proved the triangles congruent, or similar, I should say. So AEF is similar to triangle ABC. We already kind of like knew that was true, right? But now we're going to use the fact. So in step 2 here, we're going to use the fact that corresponding sides of similar triangles are proportional to then eventually prove that AE over EB is AF over FC. Okay, so let's see. I'm going to try and keep this picture nearby so that we can kind of like consider both of these at once. There we go, something like that. Okay, so AB over AE, according to our picture here, is going to equal what over here? So let's see, what's the corresponding part there? Julia. So AB over AE, what other ratio must that equal to? What does that correspond to in my picture here? Yeah, there you go. Equals AC over AF. Okay? Now you'll see here, the next step on the left-hand side of this equation, they took the AB over the AE, all right, and it changed to AE plus EB over AE by the segment addition postulate. So it looks like they took AB here and made it instead, they called it AE over EB. You see that? Those two pieces. So then AC, how can we break that down? Let's go to Lindsay. So instead of writing AC here, Lindsay, what can we write using the segment addition postulate? What plus what? So not just A plus C, those are angles. What segments can we break AC up into? So AC is made up of two segments, right? What two segments is AC made up of?
AF.
There you go. Yeah. So we can say AF plus FC all over AC. Okay. Now, why do we do that? Why do we make something that was like nice and simple more complicated? Well, because what do you see is going to happen between this AE and this AE here? What will happen here? Anybody? Yeah, they're going to cancel. And so we have AE over AE equals 1, and then EB over AE is going to be remain. And then same thing will be true. Oops, I wrote this thing down. It should be AF on the bottom. My mistake. Sorry, AF on the bottom. So the AFs will also cancel, and we'll be left with then just 1 plus FC over AF. Okay, simplification of that fraction there. All right, then if we subtract 1 from both sides, well, that'll leave us here with just FC over AF. Right? And then to get from EB over AE, to make that instead AE over EB, what's this new right-hand side going to become? Elizabeth. Sure, so for this final step here, we took this left-hand side, which was EB over AE, and it became AE over EB. So what happened there? Yeah, reciprocal, right? So what should this one then become? AF over FC, which is the thing we're trying to prove. Okay? So there we've shown that if two triangles are similar, right, in this way with a parallel line, all right, then in general, AE over EB will equal to AF over FC. Okay? So there it is. All right. So number 4 here, it says reflect, explain how you conclude, or how we could conclude that triangle AEF is similar to triangle ABC without using that 3 and 4, without using angles 3 and 4. So how could we show that triangle AEF is similar to triangle ABC? We'll still keep 1 and 2 being congruent. How can we show them similar without using angles 3 and 4, though? What can we say here? Hunter?
Angle A.
Yeah, angle A is shared by both, right? So that's angle A is congruent to itself. So angle similarity would apply, or something like that, right? We could still use angle similarity. Whoops, sorry, I'm hit off the screen there. All right, so let's blow through this here then, because I think you guys have got it, right? So there's our explanation. So let's actually do some problems here. So for example, 2, it says find the length of each segment. And so for letter A, we want to find CY. So I'll call that X here. And so, Michael, can you set us up here? We have 2 parallel lines. So this big triangle ABC is being split. The 2 sides are being split by a parallel line to that third side there. What's the ratio we could write here?
10 over x equals 9 over 4.
You got it. 10 over x equals 9 over 4. Okay, and we cross multiply, we get 40 equals 9x. Divide both sides by 9. We get x equals 4.4 repeating, I believe. Okay, you can do that in your calculator. Question? So, You could do it that way, yes. So let's talk about doing it that way. So how would we do that then? What would be the proportion we set up there? Okay, so 13 is the full length here. So we could say 13 over 9 equals what? Is x the full length of this triangle? That side? Remember, you said 10x for 10. Yeah, so what would it be there? How would we describe that? Yeah, Drew, what would it be?
10 plus x.
10 plus x, right, 10 plus x. You knew you had to combine them together, you just weren't sure how. You have x plus 10. It's x plus 10 to get the full side there. So we could say x plus 10 over, and then what would that be over? 10, yeah, because 10 is the short side, of the full side of that smaller triangle. Good. All right, we cross multiply here. 10 times 13 is 130. 9 times x plus 10. Well, which thing in here gets multiplied by the 9? Both. Good. It distributes. Okay, subtract 90 from both sides, right, to solve. I get 40. What? 40 equals 9x. We've seen that before.
So it's not required?
Nope. Not in this case, because we have parallel sides. We have parallel sides. Not always do we necessarily have those parallel sides, but sometimes we do. And sometimes, so you can use it that. So you can use this relationship when you know that these two sides are parallel like that. It cuts it into proportion pieces. So the good news is, but you don't have to. If you don't like using this proportionality theorem, you can go right back to what we've been doing too, and it still will work. We get x equals 4.4. Repeat. Okay? More than one way to do these. Okay? So thank you for that question. All right, so let's go to someone we haven't heard from yet. Keegan!
Still learning.
I got you. So let's take a look here. We'll review what Michael did, and then I think you'll be able to catch on to it pretty quick. All right, so in this diagram here, we had a big triangle, and then a parallel segment was drawn that cut the big triangle, okay, cut the two sides into like different pieces. So you got the 4 and the 9, and the 10. And the relationship here is basically that 9 over 4 has to be in the same relationship as the 10 over the x here. Okay? And so you just set up the ratio and solve it like we normally do. So looking at letter B, we want to find Pn, so here's Pn right there. We'll call that x. So what do you want to say the ratios are going to be here for that?
5 over 2.
5 over 2, great.
And then x over 3.
Yep, exactly right. See, it's that simple. You got it, okay? So let's see here, we get 15 equals 2x, and so x is 7.5. That's all. Yeah, not bad, huh? Not bad at all. Questions on any of that? We're all good? All right, flip this over here. So go ahead, take 2 seconds, do 5 and 6 if you haven't already done it, all right? Go ahead and try 5 and 6. Okay, does it say what the... Right. So would you still have those potentially? Okay. If you show them to me, I'll get the credit, no problem. And the thing, the assignment should have it written in there, like whether you, because it might have just been like you were absent or something, or I just like, Mr. Yeah, who knows? If you can show it to me, I'll give you credit, though. How about that, okay? No problem. Okay. So, let's go to Adam. Number 5, Adam. You got x equals what?
30.
Okay, can you give me the setup, please? And then we'll go from there, yep.
X over 40 equals 24 over 32.
Beautiful.
And
Whoops. Okay, yep.
I simplify 24 over 32 to 3/4.
Ah, okay, so 3/4 you said?
Yep.
That makes the numbers a lot easier to then do mentally if you simplify the ratio here ahead of time, and so then you can cross multiply, right?
I got 4x equals 120 and x equals 30.
Okay, great, very good. I like that simplification, makes it a lot easier. Okay, didn't even need a calculator then. Okay, yeah, Stephanie.
Is there another way you could have put that?
So possibly, did you get the same answer?
Yeah,
So,
I got it.
okay, so possibly then you may have found a different way to do it. So what's a different way that you set it? How'd you set it up?
I did 32.
32 over 40.
And then 24.
So that does work, yes. Okay, so if you guys want to see here, Stephanie said 32 over 40 equals 24 over x. And that, in fact, does end up working. You won't ever see me do it that way just because that's not the way the theorem says to do it. And so I'm not going to do it that way, but it does work in this case. And I think in general for these cases it will work. It should work okay. Okay. But again, the theorem states it's going to be the part of the side over the other part of the same side equals part of the side over the other part of the same side. So they like to keep the ratios using the same sides. But it still works, so.
Why are they saying it for that?
Why?
Before, weren't we, like, not getting that?
Not really, no. But again, you could have. You could have. All right, you could have. So yeah. It would still be the same thing. So yep, it would work. But anyway, okay, so yes, so x equals 30 though is your answer there. So Rn, let's go to John.
I did 5 over 8.
5 over 8?
Equal to
X
x over 10.
over 10, good.
And then it's 50 over 8.
Okay, so yeah, we get 50 equals 8x, so divide both sides by 8, and you end up with?
6.25.
6.25. Great. Okay. And so, Stephanie, how'd you set yours up here?
The same way.
Oh, you did it this way?
No.
Oh, okay. 8 over 10 equals 5 over x?
But then I changed it and it's 8 over 5. Is that still right?
Yeah, there's a lot of different ways to set these up. So 8 over 5 equals 10 over x would work. 8 over 10 equals 5 over x. That would work too. 10 over 8 equals x over 5. That would work. But what wouldn't work? 8 over x equals 10 over 5 or something like that. So you got to be careful. Not every combination will work, obviously, but there are a good number of combinations that work. So, yeah. Just be on your toes there. Any other questions for those? Again, if you always just follow the way I showed you, where it's part over part equals part over part, then you'll be good to go. All right. So, it turns out the converse is also true, which means, right, the original triangle proportionality theorem I told you guys was that if you have a parallel line drawn through a triangle, it cuts those two segments, it cuts the sides into two, proportional pieces, okay, two sets of proportional pieces. The reverse is true. If AE over EB equals AF over FC, if those two proportions are equal, then they are parallel. EF will be parallel to BC. So the backwards is true. We won't go through the proof here. I won't torture you with another proof, okay? Alright. But I do, let's see here. Want to just show here, so some examples. So for example, applying the converse of the triangle proportionality theorem. So example 4, the directions just say, verify that the line segments are parallel. So we want to verify that MN is parallel to KL. So if these things are going to be parallel, what proportions, what ratios, what things must be proportional here? So how will we set this up? Mason, how must we be able to set this up?
21 over 42
Uh-huh.
is equal to 15 over 30.
Right, and that's the key. we want to determine, are these two ratios equal? If they are equal, then we'll know that MN is parallel to KL. If they are not equal, then we can say that MN is not parallel to KL. Okay? And so how do we determine whether they're equal or not? They look like completely different fractions here, Mason, so what can we do?
You could either simplify them or cross multiply.
So which one do you want to do?
Simplify.
Simplify. Okay, so 21/42 simplifies to?
1/2.
Yeah. And 15/30?
1/2.
1/2. So are they equal? Yes. So MN, our conclusion then, that's not our final answer. Our conclusion is that MN is parallel to KL. Okay, by the converse of that triangle proportionality theorem. Okay. Alrighty. So let's do this letter B here, and then I'll get you guys started on your assignment. Okay, so last one here. Alright, so let's take a look at this one. So we're going to show that DE is parallel to AB. And all we have in our picture is that DC is 20 centimeters and EC is 15 centimeters. That doesn't look like we have enough information there, does it?
So it's not possible.
So is it not possible?
Wait,
Wait, Stephanie!
maybe the 36 minus.
Wait, where'd you get the 36 from? In directions. Oh, snap, they changed it up on us. We got to look there too sometimes. So AC is 36 centimeters. And so what'd you say you wanted to do, Stephanie?
Subtract.
Subtract.
36 and 20.
Ah, which would then give us 16, and that's the measurement of
8.
AD. Aha. Is that enough, Stephanie, or can we now set up the ratios?
No, you gotta do it for B.
Gotta do it for BC too. That's right. 27. And so, yeah, you're right there, Keegan. BE would be 12 by subtraction. Phew. Okay, and Zishan, now that we have all those pieces, what do we got to do?
You gotta put them in ratio.
Ratios. So what would those ratios be?
16.
16. Okay, good. Equals, or we want to know, does it equal?
16 equals 12.
Okay, so 12 will be in the bottom there is what you're saying. Okay, and then on top?
On top will be 27. Or no, sorry, 15.
There you go, 15, that's right. Whew. Lots of numbers going on in there, I know. There it is. Okay, Zishan, how would you like to determine if these are equal? Mason, say you want to cross multiply?
Yeah.
All right, so let's hear. 12 times 20 is?
240.
240, you got it. Okay, what's 16 times 15?
240.
240 as well. So check. So that means, what can we now conclude?
There's similar.
Not similar.
Proportional.
Whoop, we're not showing proportional. I mean, well, okay, so these two ratios are proportional. That's true. They're equal. But then from that, we can then conclude.
They're equal.
Look at what are we trying to show here? We're trying to verify that the line segments are parallel. So yes, what's parallel?
ADE and AB.
DE is parallel to AB. You got it. Nicely done. By the converse of that triangle proportionality theorem. Okay. So there you go. Questions on any of that? Mr. Witt, this is so easy. So easy. Are you sure this is honors? I know, guys. It's easy. All right.